Okay, so our next speaker is Samantha Quiñones, and she is a polyglot hacker and systems architect expert. She has over 17 years of experience. Wow, that's a lot. And she has built software and led teams for some of the largest names in financial services and digital media. Right now, she is a principal software engineer at the content platform team at AOL. Samantha is an accomplished writer and frequent speaker at technology conferences, a participant in the White House Data Jam on STEM workforce quality, flow, and diversity, and has been recognized by the Huffington Post as some of the top Latinas in American media. So I would like to present to you Samantha, and she will be talking about drinking from the Firehose, which I hope I'll understand by the end of the lecture. So go on and blow us away.
All right, thank you. Switch to my next slide. So my name is Samantha Quiñones. You can find me on Twitter at @IEatKillerBees. I have a website, and my slides are there if you're interested in looking at those things. So I'm a principal software engineer at a company called AOL. I've been doing this for a long time. I actually started programming professionally in 1987, but I've only been doing it full-time since like 1996, 1997. And I've been with AOL for about a year, and actually I joined AOL specifically to work on the project that I'm going to talk to you about. So I'm going to be telling you a story about how we approached a specific problem at AOL. So very quickly, is anyone not familiar with AOL? It's a huge thing in the States, probably not so much in Europe. I see no hands. So it means everyone's familiar? All right. I had to cut a bunch of AOL jokes out of this talk because I'm not exactly sure how well they would land, so hopefully this will be okay. So when I joined AOL last year, I was working at another company as a lead engineer. It was another media company. And they approached me seeing if I was interested in kind of coming to AOL to work on this project. And at first I wasn't. AOL's kind of been irrelevant, I guess, in the kind of the American tech landscape for the last couple decades. But I agreed. I took an interview, and during the interview, actually, I was asked a really interesting question, which was, how would you let editors test how well different headlines perform for the same piece of content? And for those of you who are involved in sort of hiring engineers, these are great questions to ask engineering candidates. It's a great way to kind of think about, to see how a person thinks through problems without sort of relying on memorization or maybe like trick questions or anything. But that aside, this is actually a hard problem in media, right? So we're trying to take more data-driven approaches to generating content. And one of the ways that we do that is through multivariate testing, which is what we're talking about here. So when we do multivariate testing, what we're doing is we're taking all of our users and sorting them into groups, right? So we have a control group, and they get the unaltered content. And then we have one or more treatment groups who are going to get content that we've altered in some way. And then we're going to measure behavioral statistics to kind of understand how the different alterations perform. So we're going to look at click-through rates, we're going to look at abandonment rates, time on page, scroll depth for each of the different groups, and then try to make determinations from that data, right? So that's kind of one way that we approach data. Primarily, my job is to ask the question, what can we learn from data? So I'm a little bit wary about the title, like data scientist or data science, which is really, really buzzy, at least in the States right now. But essentially, what we're doing is kind of looking at the data that we have, and at AOL we have a tremendous amount of it, and trying to, first of all, come up with good questions to ask the data, in the hopes of actually finding trends that mean something to us. So, like one of the questions that we joke about a little bit, and something that we're actually actively trying to answer, is what if content could change itself based on the weather? Does certain content perform better on a rainy day or on a sunny day? Do people like to read about happy things during political seasons, when they're kind of overburdened with political news that's kind of depressing and boring? From those questions, we're kind of so those are fun questions for a scientist to ask and answer. But for the business, we're actually looking at predictive analysis of quality. Like we want to take content that an editor is writing, a writer is writing about a story, and make a prediction of how well that piece of content is going to perform based on previous pieces of content that may share similar characteristics to it, right? we want to look for patterns, right? So we want to be able to identify things that maybe wouldn't jump out to a person, but that through using like machine learning, we can identify. So we can look at huge volumes of content, and we actually have a facility for doing that at AOL where basically all of the content that we generate, and we generate content for hundreds of brands, so the Huffington Post, Engadget, TechCrunch, lots and lots of different brands. So we're generating all this content, and all of it goes into machine learning, and we look at it to determine what it's talking about, what the mood of it is, how difficult is it? Is it very complex language or very simple language? And we're doing this in English. We're doing it in most of the European languages, in Hebrew, Japanese, Chinese. We're doing this at a fairly complex level. And then once we have all of that data, we run into our first major challenge, which is just dealing with big data. I said that data science is somewhat of a problematic term, and I think big data is an even worse one. When I think about big data, I'm not necessarily just thinking about large amounts of data. I think you can have big data that's somewhat small in volume, but that's very, very large in complexity. So if you imagine financial data, which I'll tell you a story about, financial data is fairly simple. It's generally just columns of numbers. There's not much to it. But you have tremendous amounts of it. So I used to work for a company called Visa. You guys are familiar with the Visa card. I used to work for Visa. And at that time, Visa processed somewhere on the order of 3,000 to 5,000 credit card transactions per second globally. So if you can imagine, each one of those transactions is a dollar figure, and we want to do statistical analysis on that, or even add it up. It's really just a problem of volume. Now for AOL, it's not so much, well, it is also a problem of volume, but for us it's more of a problem of complexity. We're collecting currently 1.3 billion events every day. And what we term an event is something happening, some interaction that an end user is taking with our content. So they may be clicking on a link. They may be hovering their mouse over an image. They may be clicking through a slideshow or a carousel. Right? So we're tracking the movement of their mouse over the screen. We're tracking how long various elements take to load. We're tracking how long people hover their mouse over different things, which actually is, we've seen to be an indicator of what they're actually looking at on the screen, right? So 1.3 billion of these events happen per day, spread over roughly 100 to 130 million unique page views. Each one of those events contains on the order of 40 data points, so some more, some a few less. So we're talking about 15,000 events every second, which contain 600,000 data points. Right? So it's a lot of data, and it's not at all normalized. Each one of these events is unique and different from all the others. Sometimes we don't get certain information. We might get geolocation information from a browser. We might get some device information if someone is accessing our content through an app. So it's coming through maybe like the Engadget app on an iPhone, and it's going through the API. We get a completely different set of data there. And for all the problems that we have storing and analyzing data at this scale, really the biggest problem is moving it. So it's moving at 25 plus megabytes per second. It doesn't sound like a lot, but when you're actually trying to do anything with that data other than just push it through a pipe, it becomes somewhat complicated. So the way that we deal with this data is through a collection farm. So we have a couple thousand servers that are publicly accessible on the internet. If you're interacting with one of our properties and you happen to have the Chrome inspector open, you'll see like calls to something called b.aol.com. Those are what we call beacon servers. There's nothing malicious going on here. Those beacon servers' only job in the world is to collect a packet of data, scrub anything that might be user identifiable, and then it pushes it onto a RabbitMQ farm. We're really not interested in who you are, just kind of what you're doing. On the other side of that RabbitMQ farm is Hadoop. So is anyone familiar with Hadoop? I see a few hands. That's awesome. Hadoop is a really, really cool framework for doing distributed parallel processing of data. Right? I said I'd tell you a story about financial services. So when I worked at Visa, we were a big data shop before there was the term big data. We had a data center and one entire floor, so about 5,000 square meters of data center floor, was tape silos. So just racks and racks of 9-track tapes about the size of a large sandwich. And they were all in these gigantic canisters, and there were robot arms inside of the canisters. And when we needed to access data, it would create a list of all of the different tapes that this data was stored on, maybe 100 or 200 tapes. And the robots would gather all the tapes, and they would pass them into an automated tape drive, and we'd load all of that data onto a temporary disk, and then we could do analysis on it. So to do that kind of stuff, if we wanted to search through the entire transaction log for a particular transaction, or take in the entire transaction log for a day and try and average out the amount of lev spent in a 24-hour period, first it would take a couple of hours to collect all the data onto a temporary disk, and then it would take a couple of hours on the mainframe computer to actually just do the math and crunch the numbers, right? Not only was it slow, it was incredibly expensive. Tape silos, I don't know if you've priced them lately, they're not cheap. They're on the order of a few €100,000 each. You needed a lot of specialized hardware. I mean, you can't just plug these into a wall socket. You need generators and power supplies and a lot of people to run these things. So it's very, very expensive. Hadoop lets us do this kind of work on commodity hardware. And nowadays, it lets us do it on virtualized hardware. So we can do this kind of stuff in AWS or Rackspace or whatever it is that you like to use, which is really, really awesome. It does this by giving us well-documented open source libraries, and then, again, optimizing for commodity hardware. It's all based around something called the Hadoop distributed file system, which is modeled after the GFS. This essentially lets us create gigantic logical files that span across multiple systems. It's pretty simple. It's rack-aware, which means that it'll try to write data into a local device and also write it into a remote device, so you have some redundancy. The big problem, or not problem, but the big constraint around Hadoop is that there is no read-write concurrency. So if you have any kind of application that needs to be writing and reading data at the same time, Hadoop is not going to be a very good solution for you. The sort of killer app of Hadoop, though, is MapReduce. This is losing some of its preeminence as things like Spark are becoming available. But MapReduce is just a framework for parallel data processing tasks. And even if you're not familiar with it, you probably are. In PHP, for example, we have the map and filter and reduce functions. These are just an implementation of sort of MapReduce. So if we have a document, I don't know how easy it is to see the text here. If we have a document, which in this case is just a string of words, we can run this through a map function and look for how many instances of a target word exist. So in this case, we're looking for is, right? So we're going to look for is. And what this map function is going to do is read through that entire string, and it's going to return a counter when it finds the word that we're looking for. We can take the output of that map function and pass it into a reduce function, and all the reduce function is going to do is take those counts and do the math on them and tell us the final number, right? So it's going to tell us that we had 2 instances of the word is, right? So this is a really simple, contrived example, but if you imagine this document not being 10 words long, but being 10 million words long, right? Or even larger, we could take that huge document, and instead of starting at the beginning and running through sequentially, counting all the instances of the word is, we can break it up into 10 different chunks of 1,000,000 words, and give each of those chunks to a single server, which will run through them in parallel, give the counts, we collect all those counts together, and then we can actually take those counts and pass them back out to those same 10 servers to do the math. They'll all sum up the counts, send them back, and we get the final result, hopefully in about 1/10 of the time it would have taken us to start from the top and move through the bottom. So it gives us a speed increase, and it also lets us do this on smaller machines, because it's a lot easier to fit 1,000,000 words into memory than it is to fit 10 million words into memory, or 10 billion words. So this is a really great solution for us. It has some limitations. So because we have this huge influx of data that goes into RabbitMQ, we actually write it into HBase before it goes into Hadoop. So there's like a buffering period until it actually becomes available in Hadoop. And even once it's available in Hadoop, we have this single gigantic Hadoop cluster that serves everybody at AOL who's doing engineering or data science. We all want to use it all the time, but we have to play nice. So it's like an old time-sharing system. Like you kind of get the time that you get. You get as many servers as you get. If you're nice, you run your jobs in the middle of the night, but even then you have to wait until the next morning to see your data. So it's at least an hour until you get anything useful, sometimes a lot more. Right, so when we ask a question like, how would you let editors test how well a headline performs? Wow, that's awesome. For a particular piece of content, that's not a question that we can answer tomorrow. Most of our articles peak within 24 hours. Actually, most of them within about 2 or 3 hours. Our editors, who are lovely people, I don't mean to make them sound demanding, they often say literally, I don't care what happened yesterday. Yesterday is gone. I care about what's happening now, right? For them, knowing how a particular multivariate test played out yesterday or last week is pretty meaningless. They want to have that information immediately. So we found ourselves in the position of having to build a real-time pipeline. So if you remember, I talked about the collectors in the RabbitMQ farm. And before I showed how this flows out of RabbitMQ into Hadoop. The nice folks who run our Hadoop cluster were very kind and built some Java streaming APIs on the other side of the RabbitMQ. So now the data is flowing into RabbitMQ, and it's flowing into HBase and eventually into Hadoop, but it's also going out to these Java streamers. And these Java streamers are really, really cool. You connect to them over HTTP, just make an HTTP GET request to them with some filters, and they start spewing data at you. The first time I ever connected to one of these APIs from Chrome, and it crashed, I knew I wanted, first of all, to give a talk on this project, and I knew exactly what I was going to call it. It's an immense amount of data that gets thrown at you. So I said about, so it's actually really interesting. I started working at AOL, but I'd been talking to my my new boss, for a couple weeks before I joined the company. And we'd actually been talking about this project and kind of talking about the requirements and where it was and what the next steps were going to be. So it was a rare opportunity to start a job on day one and literally get my employee badge and figure out where I was going to be sitting, and then immediately start working on a project. So I started working on version 1. So this is the streamer over here on the left. This is the Java streamer that I just mentioned that the Hadoop people provide. And I wanted to create a receiver, some piece of code that's actually going to make a connection to that API and pull that data in. And my initial thought was, I'm going to throw that all into a giant statsd cluster, and I'm going to let statsd aggregate all that data and push it into Elasticsearch. Why Elasticsearch? Because I wanted to use Kibana. Anybody familiar with the ELK stack? Okay, a couple people. So you know it's a pretty powerful visualization tool. If we look at it a little bit lower level, it kind of looks like this. So we have this streaming HTTP client. This was built in Node.js. So we actually just open up an HTTP stream. We're streaming in that data. We're cutting it off at the new lines because that's how it's limited. And we're pushing that onto a logical message bus. So we're just generating native Node.js events. And then I had a bunch of event listeners. I called them visitors at the time. And what they would do is pick up that event, pick up that chunk of data, do some light processing on it, generate a stat object, so create a stat record in that statsd format, and then generate an event that would cause that to get pushed out to statsd. I want to show you a snippet of code. This is the only code that survived from version 1, the proof of concept, until today, largely unchanged. It was really important for me to kind of create these little data aggregators, little data collectors in a way that was very small, bite-sized, and modular. So this is just some JavaScript code that runs and parses out the user agent information that we sometimes get out of a record, right? So this is what one of those visitors look like. So it's very, very simple code. It's not a lot of processing happening here. So this proof of concept actually worked fairly well. I turned it on, and we were getting data. So I didn't think to take a video of this, but this was a screenshot that I took on my 7th day at AOL. And it would light up the countries and show how many requests were coming in onto the platform. And the darker the country, the darker the color of the country, the more traffic was flowing from that place, right? So I was actually able to prove that we could get something meaningful out of that data. Slight problem, I was able to only pull about 300 events a second. To run this in production remember, we have a minimum of 15,000 events a second, and that's going up all the time. I would have needed at least 70 receiver servers. We run a lot of servers in production, but they're what we consider revenue-generating servers. So like the servers that we use to run PHP on and render content for our consumers, well, that content contains ads, and we make money from that. This is not making money for anybody, so 70 giant servers, no bueno. The statsd format also kind of introduced a problem in that, so when we get this data in, I know everything about this one record. So I get some information, and it tells me that an individual maybe in Bulgaria visited this particular piece of content, and they visited it from an iPad, right? So we get a lot of data that's all connected. statsd breaks that all up. So all I know is that someone visited from Bulgaria, somebody visited from an iPad, right? Somebody visited a particular piece of content. So all of that information is broken up from each other. So version 1, as a proof of concept, okay, but it was not the right path for this application. It was about this time that I kind of started thinking from an architectural perspective of how I was going to build something that would do this in an even remotely efficient way. And I started thinking about the network in terms of transits and terminals. And this is not any kind of like big data or data science terminology. This is just me making stuff up. I kind of consider transits to be short-term, in-memory, volatile storage. So places where data is only going to live for a few seconds at the most. And terminals are places where data is going, right? It's going to go there, and it's either going to get stored, abandoned, pushed onto another transit. And I came up with a sort of a maxim to guide me in building this application, where I said that I wanted to have a network of transits and terminals where no single node acted as both a transit and a terminal at the same time, right? Because there's a tremendous amount of data going through this pipeline. Everything is I/O locked all the time. I want to make sure that there was no additional CPU or I/O load that we didn't need at any single point in the network, right? So statsd immediately violates that principle, right? It acts as a transit, right? You send data into it, and data comes back out. But it holds on to it for a while, and it aggregates it. And then once a time limit has been reached or a buffer has been reached, it then pushes it, right? So it's acting as a transit and a terminal simultaneously. So for version 2, the first thing I did was get rid of statsd. And I put in RabbitMQ instead. I'm a little bit annoying with RabbitMQ. I would like to put RabbitMQ behind everything. There was a problem that came up about 2 o'clock in the morning local time, so I don't know, 5, 6 o'clock last night, East Coast US time. And I had to chime in on Slack. Well, we could use RabbitMQ to kind of pipeline those records into Mongo. Mongo is not really that web scale. It's fine. So remember, so there's RabbitMQ over here to the left of this streamer, and it goes into the receiver, into a completely separate RabbitMQ farm, which is not time shared, so I don't have to play nice with other people. This is all me, and then into Elasticsearch. Logically, not much changes. We still have the same streaming in HTTP client. It comes in, we cut the data into records. One thing that I also did here at the receiver level was I got rid of using the native node eventing. So node is really, really fast. It's really, really awesome. Events are pretty quick. But I was getting a lot of backup from that. So instead of doing it through events, I started using a process chain. So it just kind of gets pushed onto a process chain. Each individual processor picks up the record, makes some edits to it, and then passes it along, and it comes out the other side. I use RabbitMQ. If you're not familiar with it, it's because it's a very, very lightweight message broker. You can do, what I really like about it is you can do like all this complex routing in it without having to do any application level logic. And we can size it kind of on our standard virtual servers to give me about a 90 to 120 second data buffer. So if I have a network kind of glitch for a second, I won't necessarily crash RabbitMQ. So to sum up, I eliminated the data eventing in version 2, got rid of statsd, replaced it with RabbitMQ. So now my data records are whole. They're being kept together. I have all the data. And unfortunately, I lost that nice integration that I had out of the box with Kibana. One major problem here was that, I don't know if you see these two pieces of code. They do exactly the same thing. They're just kind of pulling the first element off of an array in JavaScript. This version on the right side is massively faster on the left, right? So when you start thinking about micro-optimizations inside tight loops, that's a red flag that maybe architecturally you're doing something a little wrong. This was getting very, very hairy, and I was having issues with weird, like null characters would pop up in data that was coming in, especially from like the Far East, from Japan and China. And my application would just fall over. So I started having to write more and more code that was like going into little pieces of data and like looking for weird characters and trying to filter them out, and it was very, very brittle. So I did get a lot more performance. I got up to 600 events per second out of this, which cuts the number of receivers I would need in half. But like I said, micro-optimizing all of that code was making it really, really brittle and ugly and scary. So version 2 was no good. It was time to get serious. I needed something that was going to give me very, very high throughput, something that would maybe give me the ability to do multi-threaded worker pools, which are kind of difficult. Don't let anybody lie to you. They're just as difficult to do in Node as they are to do in PHP. Something with maybe static optimization. I was going to have a very, very large amount of data in memory, so I needed something with robust memory management facilities, right? And also, I wanted to turn that receiver piece into a pure transit. I didn't want any kind of logic being done to the data as it was passing through. Also, I couldn't use Go, because no one on my team is familiar with Go. No one on my team even wanted to talk about using Rust, and I don't hate myself enough to use C. The funny thing is, when I first started working on this project, and I started talking to the people who run the Hadoop cluster, they said, "You're probably going to want to build your client in Java." And I said, "Java? It's 2014. No one uses Java. It's a Node.js world, right?" Yeah, I ended up using Java. Why Java? Solid static and dynamic analysis, both in the source to bytecode compiler and in the JIT. Has clients for everything that I need to talk to, and it's really, really well supported in AOL and in my team. It's a lot of fun to work on new technologies, but you know, if you get hit by a bus, you don't want to screw your teammates over, right? So version 3 looks fairly similar to version 2, except the receiver is now Java, and we have this new guy called the processor router up here in the right corner. That is essentially just the same Node.js code that was doing the processing, extracted into its own sort of microservice. Logically, this is the Java application is very, very similar. We're still pulling in the same stream, cutting it at the new lines, pushing it now into a work queue. So this is essentially just a big linked list. Workers pull off the queue, would generate records, push them back out. You don't care about looking at the code. I kind of call this the ketchup bottle diagram. This is essentially what it looks like. The number of queues varies based on the number of CPUs available. But essentially, we just have network input. It dumps it into buckets in a round-robin fashion, and then it kind of squirts out the bottom. Got a little bit better performance this time, 2,600 events a second. That means I only needed about 10 receivers for prod. In reality, I'm using 12, so it's pretty close. So big win, right? I mentioned that I use Elasticsearch, and that's kind of the other big piece of this. So that's moving the data. Once you've moved it, what do you do with it? Elasticsearch is kind of like a weird choice here, because we think about Elasticsearch as a search engine, and it is a very good search engine, but it's actually also a very good distributed storage engine. It clusters really, really nicely. It has lots and lots of aggregations, and it's eventually consistent in a way that works for this kind of data. I don't care about the order this data comes in. I don't care if we lose 10% of this data. Getting 1 billion events a day, I really don't care. It comes in, it gets buffered. Almost all of it gets written out within a few hundred milliseconds, and that's fine. It does all of this stuff just out of the box. So we can do things like draw a box, a geographic box given coordinates, and see all of the events that happened in that area. We can do time series and histograms. Sort of standard statistical evaluations like min, max, average. Now in the new version of Elasticsearch, we have MapReduce, so we can do really cool things like k-means analysis and stuff on data. Right through Elasticsearch, right? If you're willing to spend the time to implement a k-means algorithm in Groovy, you can do it. So this lets us ask questions like how many users viewed a particular post within, say, 10 miles of a town in Texas, right? Or what is the average time from start to start of page load to first click for readers on Linux desktops between 3 and 5 a.m. That's the money demo in media. given two sets of link text, which has the higher click-through rate for a randomized sample of readers, right? That's the multivariate testing question that I brought up at the very beginning. The important thing is that this all happens browser to browser in under 5 seconds. So if you go right now to Engadget.com and you click on a link, an editor at Engadget.com, who is in bed right now, will see that reflected in their statistics within 5 seconds, which is pretty fast, right? But is it real time? So this is a question that kept coming up over and over. My boss loves to ask me. My boss is a really, really smart guy. You'd love him. Is it real time? It needs to be native real time, native real time. And I never really understood what he did. So, like, when you think about a real time application of data analysis, who wears one of these? This is a Fitbit. A couple people? Okay. So, I mean, how does this work, right? So there's a 3-axis accelerometer in here, and it's every time it moves through space in 3 dimensions, there's some data that's being generated. And we take that huge volume of data that's being generated by the accelerometer, and we apply some algorithms to it. And from those algorithms, we can make guesses about whether a person is walking, running, going up a flight of stairs, climbing up a mountain, right? And we can take all of that data and then kind of make assumptions and infer the activity that they were engaged in, right? We don't actually know what a person was doing. We're just guessing based on patterns that we're finding in the data. And for that, you need to do it in real time. When I go like this, I want to see how many steps I've taken. I'm getting really close to 10,000. We're talking about live analysis of data as it's being collected and actively visualizing short-term trends in that data. There are a lot of problems here. So for Fitbit, it's not that bad. If your Fitbit is off by a couple steps or even a couple of 100 steps over the course of the day, who really cares, right? But we're trying to make business decisions that may impact revenue, right? So we're talking about small sample sizes for very small data sets with very small analysis windows. If you do any kind of statistical analysis, small sample sizes and small analysis windows, that's no good, right? The data volumes are way too high for any kind of comprehension by end users. And they're really too high for any kind of end-user hardware. So, like I said, when I first connected to that API, I just went to the URL in Chrome. Chrome just crashed. It couldn't handle that much data at once. So it was time for version 4. We added a WebSocket server. This is a little bit misleading. The WebSocket server actually just listens to RabbitMQ directly, but the messages that it processes come out of the processor router. Is anybody not familiar with WebSockets and like kind of how they work? A couple people. So WebSockets is really just a very simple protocol that lets the browser maintain a constant connection back to some kind of server, and it's just an open socket. Like you'd have 2 servers communicating, data goes back and forth over that server. So it allows you to have real-time 2-way communication between a client, usually a JavaScript client running in a browser, and some server in the back end. So we're just pulling this data in. It's a randomly downsampled selection of data. We push it onto an event bus, and then it gets picked up by any browser clients that are connected. We're doing the visualization here in D3.js. I'm going to jump through a couple of these slides. If you're not familiar with D3.js, it's just JavaScript. It's not intimidating. One of the first visualizations that I built was kind of a new version of that first one that I showed you. I didn't think to take a video of this. So this is a real-time visualization of traffic that's hitting our application. Right? Now, for me to look at this, I don't see anything here other than a map of the English-speaking population of the world. Right? It's very, very heavy in the United States. Really, nobody lives like kind of in that part of the United States. There's a lot of nothing right there. But, you know, Europe, Australia, that's just the map of the English-speaking world. But to the people who generate this content, this has a lot of meaning. You know, you kind of write a story and you put it out into the world, and you wonder if anybody cares, right? So this is a very live, you can make a connection to this, a human connection to seeing how your work is being actually seen and touched by other people, right? Kind of lets us see past the cold mechanical exterior of the computer. I tried to turn this into something slightly more useful. I call this the dipping dots menu, but I color-coded the pings based on the property that's being looked at. So again, there's nothing here that's really revolutionary that we couldn't infer other ways. We see like these green dots here, kind of around New York, Seattle, San Francisco, Chicago. That's one of our properties that deals with the stock market and finance, right? So financial centers. You see the yellows are Engadget.com. So people that are interested in what's going on with the new iPhone, right? So people who live in sort of places where people buy iPhones. For some reason, Autoblog, like our car property, is like really popular in Russia. It's like pops all over the place. It was fun to kind of reconnect with my geometry roots from high school geometry. You can check out my slides if you ever need to know how to calculate the positions of the vertices of a regular polygon based on the radius and center point of the polygon. It's right there. The killer visualization that people actually love, though, is this. We call it the page view heartbeat, and we actually embed this right next to the posts. Inside the CMS, they can see this little heartbeat running. And again, this is completely divorced from numbers. There's no numbers on this scale. All it is showing that people are looking at this. And it pops up, and it pops down, and it moves, and it seems really, really alive. And also, we were able to do the multivariate testing. They can do this live, and they can do this without developer involvement. They can decide, we're going to try these different headlines for this story and see how they perform. I didn't really talk much about profiling, but this is a big part of analytics, and you can't really see the text here. But we create a platform that developers develop code on. We have our own custom language that they use to build software, build applications that the end user interacts with. They don't have the same kind of tooling that we have as developers on the back end. So we built a profiler, and this captures the data as the content is being viewed and provides a developer-focused view so they can actually see which segments of their code are being executed in real time, and they can look at this as people are interacting with the software. They can see this populating in real time. So this is essentially a highly federated, multi-layer application in the end. We have a receiver layer, a receiver buffer, and a transit, a processing and routing layer, and a transit. And then it goes to storage engines and end-user consumable queues. We have a federated eventing, which I didn't have a chance to mention. Interfaces in a ton of different languages, Java, Node.js, PHP. Just yesterday, we enabled cross-platform eventing, so you can have native events from like Symfony Event Dispatcher running in PHP, interact directly with a Node.js server on another continent. So you have native cross-platform, geographically distributed eventing that's going through this same system. It's written in a lot of different languages. So it took us a little while to build this pipeline, and we have all these different entry points. We have a system that works now, and we're at the point where we've gotten through the easy part, and we have to figure out what we're going to do next. And we have a lot on our plate, and I've been able to cross some of these things off lately, like live debugging and runtime profiling, those embeddable visualizations, the federated messaging, and platform events. The next big steps are predictive performance analysis and real-time analysis. So actually being able to take this content as it's being typed out by human hands and tell them, based on what you're typing and based on what's going on in the world today, we think you're talking about a topic that people are going to engage with. We think you're going to make good money from this post. You don't want to be crass, but essentially we need to make money to stay in business. And somebody in media has to figure out how to make money from content. It might as well be us, right? Hopefully, this has been an amazing conference. I'd like to come back to BGPHP 2016 and tell you all about it. We might have a minute for questions. I'm not sure. OK, so I'll be happy to answer any questions you guys might have. If otherwise, there's my stuff. So thank you. Is there a question over here?
I have a question. Nice talk, by the way.
Thank you.
Thank you. Can you tell us approximately how much data a user transfers to a server per one page?
How much data we collect from one user?
Yes.
For an individual user, it can vary a lot depending on the device that they're on. From a desktop with JavaScript enabled and all that kind of stuff, 80 or 90 kilobytes of data. We get a lot from mobile because it's running in our native app, so we can actually do a lot of crazy stuff. For those, sometimes like 150, 200 kilobytes. So each individual data packet is not very tiny. They're pretty sizable.
do you have any idea how other big websites are processing information? For example, Russian Yandex.ru or Google, for example.
The question is, well, you heard the question. Yeah, I have a chance to come to these conferences and I get to talk to other people who are doing this kind of stuff, and more and more people are starting to look at Spark, which is a way of using Hadoop to generate sort of real-time analysis of data. Some of this RabbitMQ idea is very similar to what like John Deere is using for their, so they have like make tractors. I don't know if they have John Deere out here, but they make tractors and they're out in the fields and they have computers in them with GPS devices, so they're monitoring like where these tractors are going in the different fields on the farm. So they have also a huge amount of data. So they're doing kind of a similar, thing where they're pipelining this data and then chunking it off into little discrete services where it's needed. I don't really know what Google's doing. They're a little bit more closed off maybe than we are.
Hi.
Hi.
I'm wondering, you've mentioned that you are using HBase for storage.
Yes.
How does that fit into the Elasticsearch scheme that you just showed?
Right. So how are we using? We're using HBase. So we're using HBase essentially as a buffer to go into Hadoop. Stuff that goes into Hadoop, we can run MapReduce queries on. We can use Hive and Pig to query it. That data also gets actually siphoned off into Vertica. So we can run Vertica queries. That's like another couple hours after it's collected. You can run Vertica queries for specific, because once it goes into Vertica, it has to be very columnar, and we need to know exactly what the data looks like. So certain data goes into there. HBase itself is really only used as a buffer. So the data goes in raw, and then there's processes that basically pull it out and index it.
And are you doing a time series analytics? I mean, are you using HBase for time series, or where you're doing time series?
We're doing the time series aggregations in Elasticsearch.
Okay.
Yeah.
Hi, I have a question.
Yes.
How many of you have worked on this?
So I have kind of a weird job. So I'm principals at AOL. We kind of work on sort of one-off projects, but we have resources. So all of the stuff that I really talked about, from the streamer to Elasticsearch, is stuff that I built with occasional help from teammates. We have an entire team that I work with. It's actually part of my same organization that does the Hadoop portion of things. So we've collaborated. They've actually started using the Java client that I wrote for some real-time stuff that they're doing. So I'd say total, probably about 5 or 6 people that have had their hands in it. But the stuff that I'm talking about has been mostly me.